as well. So let's look at 51 on page 317. That caught my eye. So we're given the function y or f of x equals x e to negative 1 over x. It looks complicated. I've never looked at a function like this before. Looks complicated. We'll see in a minute. Another way of writing it, I don't know exactly which form I'm going to use when, but another form will be this. Okay, so let's get our table going with the first derivative, the function in between, and the second derivative. First, let's identify the domain. Now, if you organize your information, for example, in a table like this, you will know for sure when everything is filled out. If everything is done and it's all rows are filled up, then you know you're done. Okay, so let's start by finding the domain. What do you think? Absolutely, absolutely. Negative infinity is 0. If the function is undefined at 0, so will all derivatives. If a function doesn't exist at a point, it cannot be differentiable at that point. Good, perfect. To infinity. Very good. So now, from this, I know that x and y intercepts don't exist, because I can make x equal 0. And I cannot set this equal to 0 because x will be 0 and I'm not allowed to put in 0. So there are no x and y intercepts. Therefore, I need something to put here, 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 and here. And that's all I can find about the function from the function itself. Nothing else. So what am I referring when I say I need to put something here? Obviously, I need to find exactly. So I need to find the limit as x approaches negative infinity from, I don't know which form to use. For now, let's put this one. I may have to change it into this or something else. And limit as x approaches infinity from x e to negative 1 over x. So let's see what we have. When x, remember the graph of 1 over x. This is important to remember. It's one of those, please don't forget. So this is 1 over x. So as x approaches negative infinity, as x approaches negative infinity, 1 over x or negative 1 over x, it doesn't matter, this approaches 0. Right? So as x approaches negative infinity, x approaches negative infinity, 1 over x approaches 0. We agree? Okay. Or negative 1 over x, it doesn't matter. 0 has no sign. So what about e to 0? 1. So this is 1. And now, when x approaches negative infinity, what will 1 times negative infinity approach? Do you all agree with negative infinity? Okay. The same idea, this approaches 0 as x approaches infinity. This approaches 1 because e to 0 is 1. And then infinity times 1 is infinity. So we have negative infinity and here infinity. Is this okay so far? So that's the end behavior of the function. Obviously, no horizontal asymptotes for this function. Okay, now let's determine the limits left and right, because obviously this appears to be a vertical asymptote, so I have to determine these limits. Maybe it's a hole. I don't know. Okay, so limit as x approaches 0 from the left, from x times e to negative 1 over x, and then the other one, Sx approaches 0 from the right, from x e to negative 1 over x. So now with everything we know about from calculus, when we look at a function, before we even look or determine the first and the second derivatives, we know now to look for the end behavior using limits. If the function is undefined somewhere, we look to determine what happens left and right, using limits. Okay? Even before we attempt the first derivative or look at the first or calculate the first and the second. Okay, so let's see what happens now. As x approaches 0 from the right, from the left. As x approaches 0 from the left, this 1 over x approaches negative infinity, but there is a minus in front, so this actually approaches infinity. Not negative. Is that clear? So as x approaches 0 from the left, 1 over x approaches negative infinity, but now negative infinity times negative 1 in front will be infinity. So now, as x approaches 0 from the left, this will be 0 times infinity. We cannot conclude. This is one of the 7 indeterminate cases. Indeterminate. We cannot conclude. So I have to do something about it. I'm hoping that I can use L'Hopital's rule, but not in this stage. L'Hopital's rule requires a ratio, mandatory, requires a limit, which it is, limit of a ratio, and requires 0 over 0. This is not 0 over 0, or infinity over infinity. So, I'm going to try to change not the e to negative 1 over x, but I'm going to try to change this into limit as x approaches 0 from the left, e to negative 1 over x over 1 over x. Let's see if this is allowed, because if these two functions are not the same, then I can't proceed. So when I divide a quantity by a fraction, I have to flip the fraction, and I get x. Do you agree that this quantity is the same with this quantity? We agree. Okay, so now let's try again. When I try again, the top is still infinity, but now let's see what happens here with 1 over x as x approaches 0 from the left. So this is negative infinity. The sign is not important. It's still infinity over infinity. In this stage, I can use L'Hopital's rule. So let's do just that. So then limit as x approaches 0 from the left. I'm going to copy it because I don't have room there. Surprise, right? Okay. So I differentiate the top. I write limit as x approaches 0 from the left. E to negative 1 over x times the inner function prime. And if you remember, I said, please try to remember that 1 over x prime is negative over x squared. Yes, with minus in front because there is a negative, it's going to be 1 over x squared. It's really useful. Can you always develop it? Yes, it will take you 5 seconds. Right? You will change 1 over x into x to negative 1 and you'll figure it out in a minute, in a blink. But it's useful to remember that 1 over x prime is negative 1 over x squared. And the denominator is negative 1 over x squared. I like this. I really do, because those two go away. So now I have the limit as x approaches 0 from the left from negative e to negative 1 over x. So again, I go back to the graph. As x approaches 0 from the left, 1 over x approaches negative infinity, but with minus in front, it will approach infinity. So this will approach infinity. Then e to infinity will be infinity. With minus in front, that would be negative infinity. So one more time as x approaches 0 from the left. Yes?
So the last thing that you did when you were deriving 1 over x, they should be both negative, right?
That's a good point. Yes, they would have been without this negative at the top.
Okay.
But because there is a negative in there, when I differentiate the inner function, it will be plus. But always draw your point out something that you may. Please, I always encourage you because you may see something and I don't. It's possible, very possible. So that's why this derivative of this will be negative 1 over x squared, but it has a minus, so it's positive. So these two go away. The negative goes in front. So we have the top. One more time, as x approaches 0 from the left, 1 over x approaches negative infinity, but there is a minus. That's why it approaches infinity. E to infinity will be infinity with minus in front, negative infinity. So I go back to the table. Remember, we will catch our mistakes. If there is anything that does not match the first row, we will catch it on in a blink. Good. So now let's find the other one. I thought I chose a simple problem. My bad. Okay, so x e to negative 1 over x. Let's try this one now. As x approaches 0 from the right, let's take a look at the graph. As x approaches 0 from the right, 1 over x approaches infinity. But this one will approach negative infinity because there is a negative in front. Now, e to negative infinity, I should not write this is not legitimate. I should not write that, but okay. So e to negative infinity is like 1 over e to infinity, and this will approach 0. So this whole thing will approach 0. So x approaches 0 when this quantity approaches 0 when x approaches 0 from the right. And 0 times 0 is? Again, we'll catch our mistakes very soon, if we have any. Okay, that's all we can find out about the function from the function itself. There is nothing else. So now the next step would be to go to the first derivative. So let's look at the first derivative. I prefer this when I differentiate, not this. It doesn't matter really, but I prefer the product. So the function is y equals x e to negative 1 over x. So then y prime will be, the first function prime is 1, e to negative 1 over x plus x times e to negative 1 over x times 1 over x squared. Is this okay so far? Let's do this one more time. The first function prime is 1 times the second one plus the first function times the second function prime. E to u prime is e to u times u prime. When we differentiate this, we get 1 over x squared. Of course, I'm going to simplify 1 from here and 1 from here. I should rewrite it. I got lazy. And of course, I will factor out e to negative 1 over x. Let's see what is left in brackets. From the first term, obviously, 1 plus, from the second term, 1 over x. There is nothing else. This is out. X times 1 over x squared will be 1 over x. Agreed? The least common denominator is x, so I have x plus 1 divided by x e to negative 1 over x. Critical numbers come from two sources. From f prime being undefined, no chance. This is undefined at 0, but so is the function. So there is no critical number coming from f prime being undefined. Now, is there a critical number coming from f prime being 0? So y prime equals 0. This will never be 0. First of all, it goes to the denominator immediately, right? So this will never be 0. So what can make this expression 0? Very good. Only the numerator. X plus 1 equals 0. X equals negative 1. Yes. So I go to the table. I put in negative 1. I put 0. I immediately find the y coordinate for that point. So Negative 1 over negative 1 will be 1 e minus. So, bless you, negative e. Okay, now I have to study the sign. There is no point in studying the sign of this expression is always positive. Remember, it's graph, right? Doesn't matter. This, whatever you plug in here, this will always be positive. So this will give the sign. And this quantity can be positive and can be negative. So let's plug in a number to the left, negative 10. Negative 10 plus 1 over negative 10. What will be the sign of this expression so I can put it here? Negative 10 plus 1 over negative 10. Very good, awesome. Now here in the middle, a little, slightly difficult because I have to plug in negative 0.5. Negative 0.5 plus 1 is positive, and negative 0.5, negative. Now on the other side, let's say 10. 10 plus 1 over 10. Okay. Negative e is approximately negative 2.7. So, from negative infinity to negative e, what does the function do? Is that supported by the sign of the derivative? Yes. From negative e, which is negative 2.7, to negative infinity, what does the function do? Right. Is this supported by the sign of the first derivative? Okay. Now from 0 to infinity, increases. Okay. Let's take a look at the second derivative. I always get lazy when it comes to the second derivative. I don't want any of this, nothing. I'm going to use this. That's a simplest form to differentiate. So y prime equals e to negative 1 over x plus 1 over x e to negative 1 over x. This is what I wanted to differentiate. I don't want products. I don't want, other than this, I don't want ratios. I don't want to deal with that. So always try to find, I think that this is the easiest form. Always try to find the easiest form to differentiate. Okay, so the second derivative. E to negative x prime is e to negative 1 over x prime is e to negative 1 over x multiplied by 1 over x squared. This is already the third time we do this, right? And then plus. I differentiate the first function and get negative 1 over x squared multiplied by e to negative 1 over x. And then plus 1 over x e to negative 1 over x times 1 over x squared. So let's do this again. E to negative 1 over x is e to u times u prime. Then plus, we differentiated 1 over x, which is negative 1 over x squared, times the second function, plus the first function, which is 1 over x, times e to u times u prime. One thing I like here. Can you say what it is that I like? I know it's not fully simplified yet, but can we notice anything?
Two things factor.
1 over x squared with negative 1 over x squared, and both have e to negative 1 over x. I really like that. So this is 1 over x cubed e to 1 over x. Nice. However, this will never be 0, which is fine by me, but I need to study the sign. And for the purpose of studying the sign, I'm going to write it like this. Just for that purpose. There is nothing, no other reason why I would write this. Only because I don't want to worry about that piece. I know that x squared times e to 1 over x is always positive. Only this portion will give us the sign of the second derivative. So when x is negative, what is the sign of the second derivative? When x is negative, what is the sign of the second derivative? Of course. When x is positive, what is the sign of the second derivative? We exhausted everything. Yes, it took us 20 minutes though. Long process. Okay, so now let's graph. We start by graphing asymptotes. I did not test symmetry. If I replace x by negative x, it's not going to be symmetric. So I can write that down. So all I care about is my table. I don't care about anything else. So I see that the function is coming from negative infinity. Then at negative 1 comma negative 3 roughly, somewhere here, a little bit above negative 3. The function has a local max because the sign of the derivative is positive and then 0 and then negative. So the sign changes it from positive to negative. So this must be a bless you. So then x equals 0 is a vertical asymptote. I did not reinforce that because I already have the y-axis. So the function does this. Let's see what happens on the other side. On the other side, at 0 is 0. Open point, of course. It's increasing towards infinity and opening up. So y equals x e to negative 1 over x. I should write x equals 0 is a VA. If at least one of the two sides is infinity, that must be a VA, vertical asymptote. Any questions? Yes, please.
What is the question that would be on the test? Because I know you said that it wouldn't be the whole thing.
Yes. So one option is that I separate and I say, look at this function and give me the increasing and decreasing intervals. Then look at this function and find the inflection points and the concavity. Or I find a function that I think it would be easy or not super easy, but it will be doable in about 10 minutes. If it's not doable in about 10 minutes, then it will take you too long, and I don't want that on a test. So these are the options. Any questions on this function? So what was difficult here? These limits. These limits took us some time to find these, right? It was not trivial, a trivial situation. The limits took us some time. Then the derivative was not really very easy. If we didn't factor, we have run into problems. If I would have tried this, it would have been way more difficult to find the derivative. So always try to minimize, not being lazy, but minimize the amount of work if it's possible. So this was much easier to differentiate. In other words, this form, not this, not this. And luckily, these two cancel out. So always try not to plug in each and every piece. Try to separate the piece that is always positive, and you don't have to worry about it. Because then it makes your life more difficult. So I always try to do that and not have to look at all functions and all pieces when I determine the sign. Good. Do you think that we got the idea about these functions? I have to show a function with a rational function with a slant asymptote, however, at least one. So let's take a look at rational functions one more time before we go back to L'Hopital's rule for more examples. With my pre-calculus students, I always divide rational functions in three categories. What I call type 1, type 2, and of course type 3. No one calls them type 1, type 2, and type 3. It's just easier for me to identify with my students and say, hey, what type is it? Oh, remember such and such. Okay, so what is type 1? An example of type 1 will be x equals x squared minus 1 over x squared minus 4. What does this mean? Same degree over same degree. This is type 1. So degree n over degree n. As long as the top and bottom have the same degree, remember the function will have a horizontal asymptote. That is the ratio of the leading coefficients. We've done this when we talked about limits, when we factored out x squared, the degree of the top and the degree of the bottom, and we ended up with the leading coefficient over the leading coefficient. So let me just make it different. So if I have 4x squared minus 1 over x squared minus 4, the horizontal asymptote is 4 over 1. Horizontal asymptote. Now, type 2 has a higher degree in the denominator. So let's say x divided by x squared minus 1. What will be the horizontal asymptote for this function? And think in terms of the limit at infinities. And that will always be the answer for type 2, when the denominator is stronger than the numerator. What will be the horizontal asymptote for such a function? Of course, always. At infinities, the denominator grows so much faster than the numerator, so the horizontal asymptote is 0. And this is the only difference between type 1 and type 2. There is no other difference. The functions, of course, will look differently, but there is no other difference. This one has horizontal asymptote, leading coefficient over leading coefficient, and this one always has 0. And we can prove that by factoring out x squared, and here by factoring out x squared and top x. We did that some time ago. What about type 3? Well, type 3 is totally different. Type 3 does not have a horizontal asymptote. So a function, rational function, cannot have a horizontal and a slant. If it has a slant, it cannot have horizontal. If it has horizontal, it cannot have slant or oblique asymptote. So this is the one that is the most difficult of these three because it has a slant asymptote. We call it slant or oblique. And this is the one that I would like to work on right now before we move on to something else. On page 318, if you would like to choose, if not, I will choose. Okay, so let's look at, and this one is easier. By the look of it, 67 on page 318. So y equals x to the third plus 4 divided by x squared. So one more time, what is type 3? Degree n plus 1 divided by degree n. This is type 3. The difference in degrees must be 1, just 1 at the top, higher than the degree in the denominator. If the denominator has degree 5, the numerator has to have degree 6. Otherwise, it's not type 3. If the degree of the denominator is 2, the degree of the numerator has to be 3. Otherwise, it's not type 3. So what is special about this? Can anyone give us just the degree of the quotient? It will have a remainder, but what would be the degree of the quotient? When I divide degree 3 by degree 2. Degree 3 divided by degree 2, or degree 5 divided by degree 4. The quotient will always be degree 1. because that will be the line. So that quotient will be the slant asymptote. Now, if I have at the top degree 4 and the bottom degree 2, the quotient will not be a line. So that function will not have a slant asymptote. Okay? So degree 3, degree 2, yes, it will have a slant asymptote. Degree 4 divided by degree 2, it will not have a slant asymptote. And not a horizontal either. It's a totally different type. Okay, so we'll get to that in a minute. Of course, if I can simplify the function, I will. And here's another way, bless you, another way of presenting it as x cubed over x squared plus 4 over x squared. This is not always possible. If I have here x squared plus 1, I cannot do this. Right? If I have the denominator having 2 terms or more, I cannot do this. So this is x plus 4 over x squared. This is the quotient of the division x cubed plus 4 divided by x squared. Y equals x, which is this. This is the slant asymptote. Just the quotient. How come? So just give me the limit of this function as x approaches infinity. Where will this go as x approaches infinity? Because remember, the asymptotes, slant or horizontal, they give us the end behavior, nothing else. So when I determine the limit of this, where will this go? Exactly. That's why it doesn't count. So just the quotient of the division is a slant asymptote. Since this is a linear function with a positive slope, obviously the end behavior of our function, which is this, will be the same. It will follow the asymptote. Like it would follow if it had a horizontal, it would have to follow the horizontal asymptote. But this function doesn't have horizontal. It will have to follow the line, which is y equals x. And that would be the end behavior. That's the only discussion. That's the only difference from the other ones. That's it. So this one has a slant asymptote, and I determine the slant asymptote finding the quotient of the division top divided by bottom. That's the only difference. Everything else is the same. So let's start. Let's get the table. I don't know if when you took pre-calculus, you learned this. I did something like this with my students. But there was no way of showing them concavity, inflection points, max min without the calculator. So that was not possible then. Okay. So let's go back and identify the domain of this function. Except
0.
Exactly. So negative infinity is 0 again is the problem, and infinity. Obviously, I cannot plug in 0, but this function has x-intercept, 1. How do I find the x-intercept? So x equals 0 will be a VA. In a minute, we'll find these limits. So the y-intercept is determined when x cubed plus 4 over x squared is 0. When is a fraction 0? Only when the numerator is 0. So this is x cubed plus 4 equals 0, or x cubed equals negative 4. How do I get x? Yes, and there is only one solution. You can say, wait a minute, the polynomial has degree 3. True, but 2 of the solutions are imaginary. So I take the cube root, and I will grab my calculator and take 4 to power 1 over 3. I know it's going to be negative, so 4. What did you get? I got 1.59. So negative 1.59. Okay, so now I want to determine these. But you already gave me the answer. As x approaches negative infinity, where will this function go?
Negative.
Perfect. As x approaches infinity, where will this function go? Good. I'll make myself a note. Y equals x is a slant asymptote, because we just determined it. Now I have to find the limits here, left and right. And there is nothing else I can find about the function from the function itself. This is it. Okay, so let's find left and right. So, limit of x to the third plus 4 divided by x squared when x approaches 0 from the left, and then when x approaches 0 from the right. When x approaches 0 from the left, the top is perfect. The denominator is perfect. So I know it has to be infinity. But which sign? So now let's test with negative 0.1. Negative 0.1 to the third plus 4. Will that be positive or negative? Correct. And what about the denominator? Good. Awesome. So I have on this side positive infinity. Now the other one. Same idea, 4 divided by 0. So now I have to plug in a positive number from the right, 0.1. And the answer would be infinity. This is it. There's nothing else we can do here. Now we can move on to the first derivative. Ready? Okay. So I want this. However, I will still have to change it into a ratio when I'm done. But I prefer it over this. So the function is x plus 4 over x squared, or x plus 4 times x to negative 2. And this is what I would like to differentiate. So y prime equals 1 minus 8 x to negative 3, or 1 minus 8 over x cubed, or x cubed minus 8 over x cubed. I hope you agree in this situation, much easier than differentiating that ratio. Okay, so now critical numbers come from f prime being undefined, but that's at 0. But the function is not defined at 0. There is no discussion there. Another possibility is when f prime is 0. When is this fraction 0?
2.
Yes, when x cubed minus 8, so y prime equals 0. When x cubed minus 8 is 0, when x equals 2. We move 8 and take the cube root. So I go back to the table, put 2 and 0. I have to plug in 2 to get the y coordinate of this point. So 8 plus 4 is 12. 12 divided by 4 is 3. Is that okay? Okay, so now let's study the sign. Okay, let's plug in. I would not consider x cubed in the denominator. I will only consider x cubed minus 8 over x squared times x. And I will only worry about this, so I don't have to worry about x squared. Okay, so let's plug in a number like negative 10. Negative 10, this will be negative. And negative 10, this will be negative. Positive indeed. Will easily, very easy to catch our mistakes in a minute. It will be. Okay, now careful because I still have to plug in every possible subinterval. So I have to plug in 1. 1 minus 8 over 1, sine. 1 minus 8 over 1. That's it. And now I have to plug in 10. 10 cubed is 1,000 minus 8 over 10, sine. What type of point is 2, 3? According to this. Local? Min. Okay, now let's make sense of the first row and the second row. I'm disregarding. When I say first row, I mean the first derivative. You know what I mean. It's the second and the third. Okay, from negative infinity to 0, what does this function do? Increase. Is that supported by the sign of the first derivative? Yes. From 0 to infinity, what does the function do? Increase, and it's supported by the sign of the derivative. Now, from infinity to 3, yes, and it's supported by the sign of the derivative, and from 3 to infinity, it increases, supported by the sign of the derivative. I'm not saying it's unlikely, but I would 100%, but it is unlikely, I would say, that we make a mistake in both. So that's the way we really catch our mistakes. Now let's look at the second derivative. Do I want to look at the second derivative? Yes, because I'm going to use this, and it will be very simple. So the second derivative, 1 prime is 0, so I have 24x to negative 4, and I really like it. It's never 0, and it's always very good. Awesome. Thank you, Tom. Holds water, we say. Holds water, we say. Done. Okay, let's give it a shot. When we graph functions with asymptotes, we have to start by graphing the asymptotes first. So we have this function has 2. One of them will be an overkill. I'm not going to graph again x equals 0 because it's the y-axis, but I have to graph y equals x. So the vertical asymptote x equals 0 and the slant asymptote y equals x. I only care about my table. At negative 1.6 is 0. At 2 is 3. These are the points I have. And now let's look. From negative infinity, it crosses the x-axis, going towards infinity, increasing all the time and opening upward. From negative infinity, from close to the asymptote, asymptotically, approaches it asymptotically, crosses the x-axis, and approaches the asymptote on the left-hand side to infinity. So from close to the asymptote, crossing and approaching the vertical asymptote. On the other side, it's coming from positive infinity. It's coming to a local minimum, and you will have to approach the asymptote going towards infinity. That's why that is the trend. And this is the function f of x, x to the third plus 4 divided by x squared. Let's graph this one with the graphing calculator because you have to remember to put in the slant asymptote. The calculator will not do it by itself. So the function, don't forget parentheses around the top. X to the third plus 4, close the parenthesis, and divide by x squared, close the parenthesis. Yes, I know because it's only one term in the denominator, you don't have to. But the second one must be x. Let's say I'm going to use the standard viewing window, although I may find a better viewing window. Here it is. It's coming from negative infinity, from approaching the asymptote, crossing at negative 1.59, going towards infinity on the left-hand side of x equals 0. On the right-hand side, it's coming from infinity, coming down to 2, 3, and it has to approach the asymptote towards infinity. This gives us the end behavior, and this gives us the end behavior. Can a function cross a slant asymptote? Yes. A function could even do this. Yes. Sorry. So a function can cross a slant asymptote, and it can cross a horizontal. It will never cross a vertical, ever, because it's undefined there. But the function can do this. Why? Because when we talk about the slant or horizontal asymptote, we don't really care about this piece. But I can graph just and say to you, here, this is the slant asymptote, y equals x, and I can show you a little piece here and a little piece here. I can't do that. I have to graph the entire line. So, but here, it doesn't mean anything. So the meaning of the slant asymptote or horizontal asymptote is right here. This piece and this piece towards infinity. That's why a function can cross a slant or a horizontal, but never a vertical. Okay, so now I can put it back. Okay. Do we feel a little bit better about the information we learned from the derivatives and how we follow that summary and how we graph the function? Do we feel better about it? Would you try? Yes, James?
How again did you find the slant asymptote?
Yes. So let me give you another example. Let's look at another example to find a slant asymptote. Very good. Very good question. Let's say, what about 66? So we have 1 plus 5x, this is y equals, minus 2x squared divided by x minus 2. Perfect. So for this function, let's just find the slant asymptote, nothing else. Okay, first of all, does this function have a slant asymptote?
Yes.
As long as the degree of the top is by 1 unit larger than the degree of the denominator, the rational function will have a slant asymptote. Okay. I have two options here. I can use the synthetic division or long division. This is not always the case. The synthetic division can be applied only in this case. Whatever polynomial you want at the top, but the denominator has degree 1, and it's, for example, x plus 1 or x minus 3 or x plus 10, something like that. So in this case, we can use synthetic division. Now you would like the long division or synthetic division to refresh your memory.
I don't remember either.
Either one?
Synthetic sounds fun.
You want me to show both? Okay, very good. So let's show both. First step is what? I have to prep the function is not prepped. What do I mean by that?
Rearrange it.
Exactly. Yes, that's the key. I know it's been ages since we don't do this anymore, meaning, for example, if I want to divide 2519 by 15, I'll say 15 goes into 25 once. 1 times 15 is 15, but I need to change the sign and write 10, and then bring down the next in line, and I continue like that. So we are going to apply the exact same procedure. It will look differently because we are talking about polynomials, but it's the same idea. When we distribute back, we will have to change the sign to the opposite signs. So one more time, 1 times 15 is not negative 15, but I have to subtract. So we will follow the same step. So the same algorithm, negative 2x squared plus 5x plus 1 divided by x minus 2. The degree of the top is 2, and there are no missing terms. How do I know whether there are missing terms or not? Here's why. If the degree is 2, I expect 3 terms. Degree 2, degree 1, and degree 0. This has degree 0. So I expect 3 terms. All of them are there. What if this were missing? If one term is missing, I have to leave a blank. Okay. Now, like here, I'm asking myself, x multiplied by what is negative 2x squared? And the answer is negative 2x. X multiplied by what is negative 2x squared? The answer is negative 2x. Negative 2x times x will be negative 2x squared. Now remember what we did here? We multiplied 1 by 15 and wrote negative 15. I have to do the same thing. Multiply, change the sign, and write under like term. So negative 2x times x is negative 2x squared. But I have to subtract that quantity, and that changes into positive 2x squared. Negative 2x times negative 2 is positive 4x, but I have to change it to the opposite because I subtract. For the same reason, 1 times 15 is not negative 15, but I have to subtract. I perform the operations I see. I calculate 5x minus 4x, which is x, and I bring down the next in line. Now, x multiplied by what is x? At the top, we do not lie. So when I'm asking myself x times what is x, I have to write plus 1. Go back and distribute. 1 times x is x, but I have to subtract. 1 times negative 2 is negative 2, but I have to subtract. And this gets boxed in, because I can continue. I can't say x times what is 3. So therefore, the function that we started with now can look like this. So the function was negative 2x squared plus 5x plus 1 over x minus 2. And now this is negative 2x plus 1 plus the remainder over the divisor. Now, we did discuss this a long time ago. Can I say that x minus 2 is a factor of the top? Why?
Because there's a remainder.
There is a remainder. There is a remainder. Okay, so now can anyone read the quotient for us? Not the divisor and not the remainder, just the quotient.
2x plus 1.
Negative 2x plus 1. This is the slant asymptote. Since this slant asymptote has a negative leading coefficient, this will be the end behavior of the function. It will have to follow the slant asymptote. Is this better? Now let's use synthetic division. The algorithm for synthetic division requires us to identify A. So let me remind you, P of x divided by x minus A. When I compare x minus A to x minus 2, I know exactly that A must be, and I put it in the box. Exactly 2. Then I copy just the coefficients. If there is a missing term, I have to write 0. So it will be negative 2, it will be 5, and it will be 1. The synthetic division, the algorithm for synthetic division, requires us to copy the leading coefficient. We do not do anything to the first coefficient or the leading coefficient. Nothing. Now I multiply 2 by negative 2 and write the answer here. No more changing of signs in the synthetic division because we already took care of it in here. I perform the operations I see, and I get 1. And then 2 times 1 is 2, and this is what I have to box in. Remember, we divided degree 2 by degree 1. So this coefficient will be the coefficient of which term? Negative 2. We divided x squared by x. And there are only 2 terms. If there are only 2 terms, it must be linear. If I have 3 terms, it will be quadratic. So plus x plus the remainder over the divisor. I meant to write 1. I don't know why I wrote x. Sorry. I talked too much. Sorry about that. It's 1, of course. 2 terms, linear. And this is just this piece. Y equals negative 2x plus 1 is the slant asymptote of this function. Any questions on this?